Every Mars mission plan has the same unsolved problem sitting in the middle of it. And it's not the landing, the habitat, or the food supply. It's the 8 months of deep space transit that no current technology can make safe. Engineers have real solutions for growing food on Mars, real solutions for building shelters, for pulling oxygen out of the thin atmosphere, for landing a crew without turning them into a crater. Those problems are hard, but they're solved, at least on paper. The transit is different. The transit is where physics stops cooperating. Here's what's waiting for you between Earth and Mars. Beyond Earth's protective magnetic field, the invisible bubble that deflects most of the galaxy's worst radiation, space is saturated with high-energy particles. Not the gentle kind that give you a tan. These are atomic nuclei, the cores of atoms stripped bare, accelerated over millions of years by exploded stars, moving at speed close to light itself. They don't stop at spacecraft walls. They don't stop at your suit. One iron nucleus moving at near light speed punches through 10 to 20 of your cells in a straight line, shattering the DNA inside each one as it passes. You don't feel it. There's no alarm, no indication. Just damage accumulating silently every hour of the 8 months it takes to reach Mars, and another 8 months to come home. After 6 months in transit, your body has absorbed radiation equivalent to what a nuclear power plant worker accumulates over an entire career. And that worker gets to go home and recover. You're not even halfway there yet. The total round-trip exposure, according to NASA's own models, pushes your estimated chance of developing a fatal cancer above 5%, with uncertainty ranges that go up to 20% or higher. The acceptable limit NASA uses for career astronaut risk is 3%. A Mars mission exceeds that limit before you even land. And the uncertainty range isn't a minor caveat. It's a reflection of how little real data we have on deep space radiation, because we've never sent humans through it long enough to measure what it actually does. So the obvious answer is go faster. Less time in deep space, less total exposure. Cut the 8 months to 4, cut the dose roughly in half. The problem is the fuel math, and the fuel math is brutal. Rockets don't carry fuel like a car carries gas, where you can just fill up a bigger tank. To go faster, you need more fuel, but more fuel means more weight. More weight means you need more fuel to push the extra weight. That extra fuel has weight too, which needs more fuel. It spirals. To cut the transit time in half, you don't need twice the fuel. You need many times more. A Mars mission using current chemical engines is already 90% fuel by mass. That means only 10% of the entire rocket, 10% is crew, food, equipment, and spacecraft. There's no room for the extra fuel that would meaningfully reduce the trip time. The rocket is full. There's nothing left to add. Pause right here. You're designing this mission. You have one option left. Add water walls around the crew compartment to shield against radiation. But every kilogram of water you add is a kilogram of fuel you can't carry, which means the spacecraft gets slower, which means the crew spends longer in deep space, which means more total radiation exposure. More shielding might actually increase the total dose, not decrease it. Where do you think the tipping point is? Does more shielding always help? Or at some thickness, does it start making things worse? Think about it before you continue watching. Here's what shielding actually does in deep space, and it's not what you expect. On Earth, you stop radiation with lead. Dense material absorbs the particles and they go nowhere. In deep space, the particles are so energetic that when they hit dense shielding, they don't stop, they shatter. A high-energy cosmic ray hits aluminum plating and breaks apart into a spray of secondary particles, fragments, neutrons, smaller nuclei, all moving in different directions. Some of those fragments are more dangerous than the original particle. You've turned one bullet into a shotgun blast. The materials that actually work against deep space radiation are hydrogen-rich ones: water, polyethylene, liquid hydrogen fuel. Water walls genuinely reduce exposure without creating the secondary spray problem. But to provide meaningful protection, you'd need roughly 1 meter of water completely surrounding the crew compartment on all sides.
That's tens of thousands of kilograms of water on top of everything else you're already carrying. And even a full meter of water doesn't block everything. It reduces the dose by roughly half, not eliminate, half. NASA's own models show that even with heavy water shielding, a 940-day Mars mission still puts estimated radiation-induced death risk above 5%, with upper uncertainty bounds near 20%. That's with the best shielding currently practical to carry. The shielding helps, it doesn't solve the problem.
There's also a second damage pathway that doesn't show up in cancer statistics. Recent research suggests high-energy cosmic ray particles damage brain tissue in ways that don't produce tumors. They produce cognitive decline. Subtle, permanent changes to how your brain processes information. The damage doesn't show up for years. You land on Mars, you do the mission, you come home. 2 years later, your memory is worse. Your reaction time is slower. Your ability to focus has dropped. Nothing you can point to, nothing a doctor can fix. Just a quieter version of yourself, produced by 16 months of particles passing through your skull. There's no shielding currently planned that addresses this. It may be unavoidable with any currently proposed mission architecture. Here's where it gets uncomfortable. NASA says the acceptable risk threshold for radiation-induced death is 3%. A Mars mission produces 5 to 10%, possibly more. You're the mission director. You have 3 options. First, delay the mission indefinitely until better propulsion technology is developed, which has no timeline and may never arrive. Second, lower the acceptable risk threshold to match what's actually achievable, which means officially deciding 5 to 10% chance of killing your crew with cancer is acceptable. Third, ask for volunteers who explicitly accept the elevated risk as a condition of selection, which some researchers argue is the only ethical path. All 3 are real positions, held by actual people at real space agencies. Which one do you choose? None of them are clean. Nuclear thermal propulsion, a type of engine that uses a nuclear reactor to heat fuel instead of burning it chemically, could cut the 8-month transit time to roughly 5 or 6 months. That's a meaningful reduction. It drops total exposure noticeably, but it doesn't solve the problem. 5 or 6 months is still enough for radiation to push the mission past the 3% threshold. You've moved the number, but you haven't moved it past the line. There's one propulsion concept that could actually clear the threshold: nuclear pulse propulsion. The idea is to detonate a series of nuclear explosions behind the spacecraft, using the pressure wave from each blast to push the ship forward. The math works. A 6-week transit to Mars would cut total radiation exposure by 90%. The physics is real. The problem is that nuclear pulse propulsion requires detonating nuclear devices in space, which violates every international treaty on nuclear weapons beyond Earth's atmosphere. It's not a banned technology because it doesn't work, it's banned because it works fine, and because the world decided in the 1960s that nuclear weapons in space were more dangerous than useful. To use nuclear pulse propulsion, you don't need a physics breakthrough, you need to rewrite international law. Here's the final trade-off, and it's the most honest version of the question. Nuclear pulse propulsion could get a crew to Mars in 6 weeks. It violates treaties that govern nuclear weapons in space. Option A, rewrite the treaties to allow it, which means accepting that any nation with nuclear capability could use the same technology to put nuclear weapons in space with plausible deniability. Option B, accept the current mission mortality risk and go anyway. Option C, decide that Mars isn't worth either compromise and wait for a propulsion breakthrough that has no development timeline. There's no safe answer here. Physics forced you into a political question that nobody in any Mars announcement ever mentions. Some researchers have proposed a partial workaround. Send only older astronauts, people whose reproductive risk is lower and who have statistically fewer years left to lose to cancer. The Mars 500 simulation, 520 days sealed in a habitat to test psychological endurance, found that the psychological degradation from long confinement is real but manageable. One crew member showed signs of depression during more than 90% of mission weeks.
Two others developed persistent sleep disruption that lasted for months. But people managed it. They stayed functional. The psychological math, difficult as it is, can be worked. The radiation math, without better propulsion, cannot, because it's not a human endurance question. It's a physics question. And right now, the physics says the number exceeds the limit regardless of how mentally tough the crew is.
The problem that makes Mars unreachable isn't engineering, it isn't money, it isn't courage. It's that every Mars mission proposal that sends humans through deep space and back produces a radiation-induced mortality risk above what any space agency currently considers ethical, and there's no propulsion system on Earth right now that changes that calculation. The only thing that changes it is a propulsion breakthrough that hasn't happened, or a political decision to accept the elevated risk and go anyway. Both are possible, neither has a schedule. Until one of them materializes, every Mars mission timeline you've ever read is built on an assumption that the radiation problem will be solved by the time the mission launches. That assumption has been in every plan since NASA published its comprehensive radiation risk analysis in 2013. The conclusion of that analysis was careful, precise, and devastating. With the best available shielding, the best available propulsion, and the most favorable solar conditions, a Mars round trip pushes estimated fatal cancer risk above the 3% limit. 13 years later, that analysis hasn't been superseded. The number is still above the limit, and the problem is still unsolved. The irony that doesn't make it into the announcements is the harder you try to solve it with engineering, the worse the engineering trade-offs get. More shielding means more weight, which means slower speed, which means more time in the radiation, which partly cancels the shielding benefit. More fuel means faster transit, but leaves less room for everything else. Every exit the engineers open leads to a new wall. The physics locks the outcome into a range where the best achievable result still exceeds the threshold. You can optimize inside that range, you cannot escape it, not with what exists now.